exam 2 in this class. However, I think you all did well. These are the stats for exam 2. The average was 72%. We had a few 100, which was very good. The lowest score was 31. Now, again, these are the grades based on Canvas, and we'll talk how we're gonna adjust these grades. Standard deviation about 16 points. So many of you are between 72 and 72 plus 16, right? Like we learned, but many of you are below average, essentially nearing C minus. The average time was about an hour and a half. Now, as I promised, I was telling Katrina earlier, I promised you early on that we'll do a lot of partial credit for exams, but no partial credit for homework. And this still stands. However, this is going to be a little bit harder to do this time because these online exams are low stakes exams, right? So they have a lot of questions that are true or false, or pick from the following, or do a small derivation, right? So we had 17 questions, and if you hadn't noticed, many of you, well, on many problems, most of you got different numbers in the question, because there's a cool thing you can do with Canvas where I can program different numbers. So, you know, your answer may be different from the answer, your correct answer may be different from the correct answer for your colleague or friend, right? So that makes the cases of looking through your derivations extremely, they just blow up exponentially. I calculated an estimate of how many variations I have to go through. It's probably 2,000 variations. So rather than going and giving you partial credit myself, which would take me probably a year to go through all the problems, I'm going to put that burden on you. And you already had started contacting me about partial credit for some problems. And especially because you know what you did, you know better, you know best what you did and where you feel kind of you missed an answer, for example, right? So I'm going to give you until, I'm going to give you the opportunity to reclaim partial credit. You can open up a case just by emailing me directly to my work email, tony.saad@kamenge.utah.edu. Make sure you put this subject line so I know how to, you know, just separate your emails into a folder and then go through them and address your concern. Make sure the subject line is exam 2 partial credit, hyphen, put your name. And then in the email, explain in details, like, you know, these are the questions where I feel I deserve partial credit. Question 1, on the worksheet, which I have, right? And you have too, but you scanned it and sent it to me. In exam 1, you know, I put this answer. However, in my derivation, I had another answer. I made a mistake by copying. Would you please look at that? Question number 4, you know, this and that, and then make your case. And then I will look into it and give you as much partial credit as possible. And I'm very generous with partial credit, as long as you've shown that, you know, you understand the methodology. You're not just punching numbers randomly, right? You will get, you will not be penalized for missing a right answer. But you'll have until Friday, April 3rd, tomorrow, midnight, to make your case or to contest your grade in any way. If you have any question, any concern beyond that, you know, I'm not gonna be taking cases, okay? So go through your exam, your worksheets, go through the answers, and if you feel you missed the question here or there, it doesn't hurt to email me and make a case, okay? So hopefully that's clear for everyone, and we can get into finishing off with our course. What follows are the last few topics we're going to cover in numerical methods, and those revolve around differential equations, okay? And specifically, we will focus on ordinary differential equations, but I'm going to take this opportunity to give you an engineer's perspective and sense and feeling of what a differential equation is. I know many of you are taking ODEs or have taken ODEs, and you know probably how to solve an ODE or a system of coupled ODEs, etc. But my guess is that, and myself included, you never got a sense or a feel for why do we need differential equations? Why do we need ordinary or partial differential equations? And how do they show up? And what is their purpose, right? And why are they so powerful in describing the entire world around us, okay? And as we've been accustomed in doing, we're going to look at the learning objectives first. So this will give you kind of a bird's eye view of what the goals of this chapter are. And you'll be able, at the end of this chapter, you should be able to define a differential equation. That will actually be the first question on the next slide, okay? You'll be able to define and identify what we mean by a dependent and independent variable, what are the coefficients in a differential equation, and what we mean by the right-hand side of a differential equation. Distinguish between a partial differential equation and an ordinary differential equation. Identify and classify ODEs. So are they initial value, boundary value problems, first order, second order? Identify initial and boundary value ODEs. So that kind of follows up with the classification. Describe the meaning of terms in an ODE. And I'm gonna spend a few slides on that. And we're gonna do something really cool by looking, by interpreting any type of ODE, by looking at population dynamics. Okay, and the video behind me is showing a population of Paramecium, which we're gonna try to solve together in a little bit. Okay, create Python code to solve a single ODE or a system of ODEs. So we're gonna invert things in these lectures rather than, if you remember in the previous lectures, we always had a slide called Pythonification, where we would first, before getting to Python, we would first develop an algorithm, develop our own code, and then see how we do it in Python. In these lectures, we're going to do it the other way around because our code is going to be so complex. It's going to be much easier to kind of get a sense and feel and excitement about results before we start programming the methods ourselves, okay? Then we will learn how to use explicit and implicit finite difference methods to calculate a numerical solution for initial value problems for a single equation and a system of equations as well. We'll use finite difference methods again to do boundary value problems. And those are going to end up with a system of linear equations again, as we've been used to. Identify when the right-hand side of an ODE is nonlinear. Now you have familiarity with that based on what we did with regression. You can understand kind of what is linear and what's nonlinear. And calculate a numerical solution for an implicit method with a nonlinear right-hand side. This is going to bring in Newton's method, which we covered in the last chapter. And finally, linearize a nonlinear source term for a boundary value problem. We are going to begin our lecture with an activity. Now, these activities are in groups when we were physically present in class. So if you are in groups, work together in group. I want to hear some buzzing like I used to hear in class. But if you're by yourself, just do it by yourself. You can speak to yourself if you want, that's okay. And then I'm gonna pick one of you to get an answer. And the first activity is, what is a differential equation? So go on, take a minute and think about an answer and be as rigorous as possible, excuse me. I have my timer here. Okay, you're almost out of time. Okay, time. All right. So do I have any volunteers? Looks like I have a volunteer. Yes. Hello? Brandon? Okay.
Hi, yeah, I'll answer.
Yeah, go ahead.
That relates a function to its derivative.
It relates a function to its derivatives. Yes and no, but what is that function? So you're right in terms of derivatives, but what's the function? What about any other takers?
Can you guys hear me?
Yes.
Oh, cool. So isn't it a function that's dependent on its derivative? Or the derivative is
Yes,
incorporated in it?
yes. So you both are kind of correct, but the definition is a little bit off. So let me give you a slightly better definition. A differential equation is just an equation with terms that involve derivatives of a quantity. Okay, so like you said, it's an equation that has a function and its derivatives. It's just an equation with a bunch of derivatives in it. So how does it look like? I'm going to give you a specific example, which we will address later on in the course. If you look at this is a differential equation. You probably can tell that this is a differential equation. It's an equation that has derivatives in it. Some of them are second order, some of them are first order. The dependent variable is usually the function that is being differentiated. So in this case, this would be t. Okay, and that's just some definitions we're going through over here. Okay, the independent variable is usually what we're differentiating against, right? So it's d by dx or d by dy, d by dt, right? Whatever, it's just a variable, but that variable is usually independently chosen. So you choose, for example, if you have a time-dependent differential equation, you choose the time over which that equation is valid. Could be, from time t equals 0 seconds to 360 seconds. You're running an experiment, for example, or a reaction. And then the things that multiply those derivatives are called the coefficients. Now, those coefficients don't have to be constant. They can be constant. They can be a function of the function that is being differentiated. So in this case, they could be a function of t, and they can also be a function of the independent variable, such as x over here, okay? Okay, great. So now the main question is, why do we develop equations with rates of change in them? I'm going to give you the answer, but then we're going to dig deeper to actually motivate you for why this answer is valid. The reality is, it is much easier to describe natural laws and complex systems by looking at the rates of change of quantities and relating different rates of changes to each other, rather than looking at a specific value of the quantity itself. Okay, so let's do an example. We're going to start. I think the best way to explain differential equations is to look at population dynamics, and essentially population dynamics tell us about how populations grow and multiply. Okay, and so we're going to do just that. Okay, and we're going to approach this in two ways. We're going to look at how a population grows by trying to develop a formula without using differential equations. And then we're going to hit a point where like, we can't develop a formula anymore. This is too complex. And then we'll see how much easier it is to develop a differential equation and solve that differential equation. Okay. So we will start by looking at a population of Paramecium. It's a unicellular organism. It's just right there behind me. You can tell them hi. And these unicellular organisms, they typically divide once per day. So each one of them kind of separates into two per day, and then each one takes another day and separates into two. And you can see how that population can explode in a matter of a couple of weeks. That population could grow extremely unbounded. So starting with a single individual, for example, at day 0, we expect in successive days to get 2, 4, 8, 16, etc., etc. Okay, so now our goal is to develop a formula for the population of Paramecium. Okay, so if we start with a P0 initial population, could be 1 individual or could be 10, we're going to call that P0 as our initial starting population. And then after 1 day or 1 interval of time, that population becomes 2 times P0, correct? Because each one of those individuals initially is going to divide into 2. So if you had 1 individual, after 1 day, you're going to have 2. If you had 2 individuals initially, after 1 day, you're going to have 4, and so on. And then after 2 days, we double what we had on the previous day, right? So P2 becomes 2P1, and that's equal to 2 squared times P0, right? We're trying to relate everything to that initial population. Okay, so now your activity, again, you can do it in groups or individually. If you are in groups, do it in groups. You got 1 minute. My question to you is, after T days have passed, so T could be 50 days, right? I want to know how many individuals are there after T days have passed, given that the initial population is P0. Okay, so continue that recurrence formula and find me P after T days. You got 1 minute. I want to see you working on your sheets. So one tip is just continue the recurse formula, P3. What is P3 in terms of P2? And go back all the way to P0. And then the formula is just going to pop up in front of you, okay? Get 10 seconds. Okay, time. All right, so let's get our wheel of names out here so that I can randomly select some of you. Okay, let's get the wheel of names over here. Okay, now most of you are not present, but let's just spin it. Okay, Brian, are you here? I think I thought.
Yes, I'm here.
Yes, go ahead.
So I put P of t equals 2 raised to the t times P0.
Absolutely, you are correct. And I hope that most of you got that answer. Okay, so what Brian said is that after t days have passed, the total population is 2 to the power t, where t is the number of days, times P0. And the way you do this, you just carry the recurrence formula for 3 days, which is 2p2, and then you express that in terms of p0, and then the pattern emerges very quickly. Okay, that's not too bad. That's pretty easy. Now let's go a little bit further. Okay, so okay, hold on. I'm having issues with my keyboard. Okay, so pt is 2 to the power t p0. Now in general, that 2 to the power t, that 2 only applies for like bacteria and unicellular organisms that divide into 2 and keep dividing into 2. But in general, for example, take a population of lobsters, Connor. A population of lobsters does not necessarily divide that way, right? So, the lobsters have to mate and get married and have children, and, it's kind of the rate of growth is very different, right? So in general, what we want is to say, regardless of what organism, there's a certain rate of growth. Could be 1.1, could be 17, like rabbits. I don't know how fast they reproduce, or mushrooms. Mushrooms, they reproduce really, really quickly. So in general, we can write for a population that has, we can say a population that has a growth rate R. After t days have passed, that population is equal to R to the power t times P0. P0 is the initial population. Okay, agreed? Does anyone disagree with this? Okay, good. No disagreements. Okay. All right. So now I want to take this one step further. I'm just going to do a sleight of hand just to rearrange the mathematics a little bit. Obviously, that number R could be expressed in an infinite number of ways. Okay. So one way that I want to express it in is using exponentials. And conveniently, we can write R, capital R, as e to the log capital R, correct? And let's call capital log R as lowercase r, so that we can write the total population as e to the RT times P0. All I did here was take R and write it as exponential to the log R. Nothing. And then I called log capital R, I called it lowercase r. It's just a simple manipulation. Now, why did I do this? Because exponentials are cool. They're nice. They allow us to use calculus. Their derivatives kind of don't change. They're like the same. It's just much easier to deal with exponentials. There's also another reason that you will recognize once we hit differential equations, okay? Now think of R. R for population dynamics, R is called the intrinsic rate of the population, and sometimes that's not clear. But a better way of explaining what R is to think of compound interest. If you have money in the bank and you say you're earning an annual interest of 12% on that money, and that interest is compounded daily, okay? R is that 12%. So think of a population, say that it grows by 12%, so 0.12, put 0.12 over there, and that would give you that population growth, okay? We're good so far. So now we're going to switch from the Paramecium, where the growth rate was specifically log 2, right? Lowercase r was log 2. Now we're going to stick with lobsters, okay? Now the power of this equation is that it tells us things about the population. Okay, so again, you know, I'm not talking about this course is not about population dynamics. Okay, but I'm trying to get you comfortable understanding populations because they're going to help us in understanding ODEs later. Okay, so if you plot the population versus time, you have three scenarios over here. If R is positive, what's going to happen? That population is just going to grow unboundedly, right? It's just going to keep growing. You have an exponential growth. That's what we call exponential growth, right? If R is 0, in other words, there are, for every lobster that is born, a lobster dies or is eaten by a red lobster, you know, or something, right? For every lobster that's born, a lobster disappears. Or think of a population, right? For every birth, there's a death, okay? So that makes R equal 0. There's no growth in the population, and that population remains constant throughout time, right? But there's one more scenario. If R is negative, it means there's more death than there are birth, and that population is gonna dwindle. It's an aging population, okay? Just a comment, that's a comment on the side. Okay, now in reality, okay, populations do not grow unboundedly, okay? If you have a healthy population with birth and death rates, typically that population is gonna reach an equilibrium because there are limited natural resources and environmental constraints on that population in terms of food and etc. So food and resources can be depleted over time, and naturally that population starts kind of reaching an equilibrium point. And pardon me, if you look at the graph to the right, that's very likely what happens in reality, and actually what we observe in animal populations. Initially, there is exponential growth kind of over here, close to P0. There's exponential growth, but then as the population grows and grows and grows, it's going to reach an equilibrium point, and the net growth, so in other words, there will be probably more death and less birth, or either one of those, and then that population is going to reach an equilibrium point K. Okay, so all right. Now my next challenge to you is, and this is actually a challenge, assume that due to food restrictions, a lobster population with intrinsic growth rate R, so that's e to the R, right, cannot grow beyond K individuals, whatever K is, okay? I want you to take 2 minutes now and try to develop a formula for the population of lobsters as a function of time, such that they're gonna reach a plateau at K. So go ahead and give it a shot. You got 2 minutes. So try to use the recurrence formula, something similar to what we did before, okay, and see if you can get to an answer. So if you can actually get to a formula with that, I will give you an award, unspecified award. You got about 45 seconds left. All right, time. Let's see. Okay. Do I have any volunteers with an answer to this question? Okay, I see Connor and Abigail. They're nodding their heads. Katrina is shocked. Okay. I guess no volunteers.
I mean, I don't have an answer, but you just have to approach it as t approaches infinity,
Okay.
right? I don't know.
Okay. So the reason I didn't pick anyone is that this is actually a very difficult problem to solve, right? To solve this way. I have no idea how to approach this. Even starting with the recurrence formula, I don't have any idea how to approach this. It's not clear to me. Now the
Could you-
formula, yes, Emily?
I was thinking of something say like using the Hill function, where it's like k is over to k plus r, and those are kind of like specified. But then like I didn't remember the equation exactly, so I was like, eh.
Okay. Okay. I mean, it's possible to probably derive it this way, but it's kind of annoying, right? It's impractical when the population growth gets complicated like this. You'll find it's very impractical to derive an equation for the population this way. Now, the formula for this case is this formula. Okay, it's P of t is P0k over P0 plus, et cetera, et cetera. Now, what happens when P reaches k? Okay, when P reaches k, the population becomes equal to P0. Okay, the population becomes equal to P0. Now, how do I get this formula? That's going to be our next set of slides. Okay, so the point right now that we made is that as you complicate your system, as the system becomes more complex, it becomes harder to find a solution for whatever you're looking for. In this case, we are looking for the population size. We put constraints in the system, and we're like, wow, and this is only a slight constraint. What if you're going to add now a time-dependent availability of resources, for example? Or what if you're doing this for the spread of an outbreak, like the current outbreak? You know, how do you predict the number of people being infected and people coming in and traveling and people being vaccinated and people developing immunity? It is nearly impossible. It is actually impossible to do it this way, okay? But what I want to introduce to you today is another approach to do this. Rather than looking at the population itself in our derivation, why don't we look at the rate of change of the population? So rather than saying we are interested in finding out what the population size itself is, let's see and think about how that population changes over time, okay? That's what differential equations are, okay? So now, as a warm-up, the first thing I want you to do is, again, do an activity. You have 2 minutes, maybe 1 minute, actually. I'll give you 1 minute. There's a typo here. Let's do 1 minute. Consider a population of lobsters with an initial size of P0. The birth and death rates of lobsters are equal. So for every lobster born, a lobster is eaten, okay? So that their population remains constant over time. Now, I want you to develop an equation. This is the first differential equation that you develop. I want to develop an equation for the rate of change of the lobster population, P, over time. So I want to develop an equation for dP by dt that describes this lobster population that doesn't change over time. Go. And if you find an answer, even before the time ends, feel free to speak out. Here you got 15 seconds. Okay, let's get to our wheel of names. All right, time. Okay, so let's spin the wheel. Okay, this is going to be difficult sometimes this week. Okay, Isabel, are you here? Let me see. Isabel is probably not here. today. Okay, let's pick one more person. If not, we'll. Okay, Taylor. I can't see through the participants. Let's see, Taylor. Taylor is not here. Okay, so I'm just gonna pick one of the available. Henry, are you here?
Yeah, I'm here.
Yeah. Do you have a solution?
So wouldn't the delta P just equal 0 because there's no change over time?
Okay, so what is that? What do you mean by delta P?
Well, the rate of change of the population of lobsters.
Okay, that's right. So Henry's answer is to say that since the population of lobsters doesn't change over time, then the rate of change of the population of lobsters is 0. dp by dt, okay, is equal to 0. So I want you to pronounce it correctly. Rather than delta p, you should be specific and say dp by dt. Now, delta p is strictly reserved for numerical methods. So I would rather use dp by dt or partial p by partial t as we go to partial differential equation. But in this case, you should say dp by dt is equal to 0, which implies that p of t, the solution to this ODE, is equal to a constant, and that's equal to p0, the initial population. Okay, great. Now let's take this one step further, and let me move this window out here. Okay. So now your second activity, so now we're building up. Now we know how to create a differential equation, just 0 on the right-hand side. Now assume that the lobster population changes at the rate r. So think of this as the compound interest yearly, so that per unit time, r times p lobsters are born or removed from the population, depending on the value of r, okay? So if r is positive, r is negative, okay? So now develop an equation for the rate of change of the lobster population over time, again, but such that they change by rp, okay? So go on. Got 1 minute? Again, now we're developing equations for the rate of change of the population, not the population itself, okay? The rate of change of the population. Okay, time? All right. So Ryan, do you have an answer?
Yeah, dp by dt is equal to r.
Okay, why r?
Because if you...
Does anyone disagree with Ryan's answer? So the change in the population is dependent on the population itself. It's not constant. So for example, if there are more lobsters, they're again gonna date and marry and have more children, right? So that's gonna be more, and they're gonna produce more, right? So the rate of change of the population is a function of the population itself. Nick, do you have a correction? Let me unmute you. Yeah. Oh.
Okay. Could you just so if we use the same term as so before we had e to the power of RT. So
No,
would it be e to the power?
I'm not looking for an answer for the population. I want a differential equation for the rate of change of the population. And I'm telling you that the rate of change or the population changes by r times p. Garrett, do you have an answer?
So I was thinking it would be P naught times by RP, and P would be birth minus the death rate.
So what is your differential equation?
Let's see. So dP by dt equals P naught times PR.
Times r times p. Okay, so you're almost there. but you don't need to include the P naught. The reason you include the P naught is because you've been biased to develop algebraic equations. For a differential equation, that P naught initial condition is going to be part of the solution automatically. So let me give you the answer. The rate of change of the population is simply R times P. That's all. That's all there is to it. In any interval of time, wherever you are in that population path, okay, that population is going to change by the growth rate times the value of the population. So in other words, our ODE, our differential equation, is simply dP by dt equal RP, right? So you almost got it, Garrett, but you didn't need to include that P0. Because once we solve for that ODE now, the solution is some constant times e to the RT, and that constant is equal to the initial condition, if you remember your ODE courses. So we're not gonna solve ODEs analytically here, but that's kind of as simple as it gets in terms of ODEs. Now this is, if you remember, this is the solution that we got earlier when we did the problem for the Paramecium, right? When we had R to the power T, R to the power T times P0, and then we wrote R to the power T as e to the RT. That's the solution that we got there. However, now we developed this from a differential equation. Now compare and contrast the work it took to develop this equation, develop the previous equation. Previously, we had to do a recurrence formula, P0, P1, P2, P3, and then P at T, right? So we had like a few lines. Over here, all you needed is one line to write the differential equation, and then another line with the solution, right? And you got the same answer, okay? So that's, you can start seeing now and sensing the power of differential equations. But you have to start thinking in terms of rate of change rather than the population itself, okay? So now we're gonna go to the next challenge, which we couldn't find a solution for using the other approach, right? And you're probably, it's gonna be probably as hard on you here, but it at least is a path to get a solution. So now assume the population cannot sustain more than K individuals. That's called the carrying capacity, FYI. So again, we wanna try to model that growth. So now my challenge to you, and I'll give you 2 minutes because it's a little bit harder this time, is I want you to develop a differential equation. So stay with dP by dt equals something. So we started dP by dt equals 0 for a constant population, and then dP by dt equal R times P. So there's always a growth rate going on times the population itself. Now I want you to take that equation and extend it so that the population growth looks like this. When you reach K, the population doesn't grow anymore. Now think in terms of rates of change. Initially, the population is growing exponentially. So initially, it's like going as RP on the right-hand side. The rate of change is R times P, right? But as you reach K, what happens to the rate of change? It goes to 0, right? So you kind of need a switch on the right-hand side, a continuous switch, such that early on, it's kind of close to R times P, and then later on, it turns to 0. And I'm giving you a tip here. If you take the previous equation, dP by dt equal RP, change R, make it something that looks like this form, R into something minus P, such that that goes to 0 when the population reaches K, okay? So go on, you got 2 minutes. And I already started the timer, so I'll restart it over here. Okay, some of you actually are kind of getting to the answer. So I'm going to pick you to give the answer. Okay. You got 40 seconds. Please don't chat your answer. Let's give a chance to your colleagues to actually think through this. In the meantime, I'm thinking who I'm going to pick for this. All right, you got about 3 seconds. And time. All right. Let's see. Rachel, are you with us?
Yes, hi.
Hi, Rachel. Okay, do you have an answer?
Yeah, I was thinking R times K minus P times P.
Times P.
Yes.
Yeah, so yeah, that's right. So that's, you just spelled out the full right-hand side, exactly. So you got dp by dt, R into K minus P times P. So why did you choose that? Why did you choose that answer? Why did you choose K?
Because that's the max, I guess. So you can't
Yeah,
like go over it.
Yeah. So when P approaches K, the entire growth rate becomes 0, so the population doesn't grow anymore. So Rachel is correct. So what we're going to do, we're going to take this equation, dp by dt equal R to the P, and we noticed if you remember when I discussed the different options with R, everything depends on this R, right? And R doesn't have to be a constant. Could be a function of time, right? Could be a function of P itself, right? Could be a function of the population or anything else. So what we did here, we're going to take this R and turn it into R, some other growth rate, times K minus P. So the constant value in R doesn't matter. What matters is the form, okay, the structure, the shape. So this one has R times K minus P. Now what happens in this choice is that when P approaches K, that entire growth rate becomes 0, so that the rate of change becomes 0. And that's what matters. That's the power of rates of change. So now our full equation becomes this guy, right? And again, when P approaches K, it's going to flatten out because dp by dt, the rate of change becomes 0, okay? So now given this, you have, it's not an activity. Let's not do an activity on this. Let's just discuss it together. What happens to the population here, just by looking at the differential equation now, we haven't solved it yet, but we have an equation now that describes how this population changes. Initially, when the population is small compared to K, K minus P is dominated by K. So then your right-hand side is R times K times P, which gives us exponential growth. It's a constant times P that gives us exponential growth. And that's what we expected. Initially, we had exponential growth. But as P grows, and as it approaches K, K minus P approaches 0, so that this entire term on the right-hand side approaches 0. So therefore, there's no more rate of change anymore. It's not changing. The population is not changing anymore, and you get this kind of nice shape that plateaus at K. And if you solve this equation analytically, this is the formula that you get. Okay, and this is how I actually got that formula. I took this equation and put it in Mathematica, and I asked it to solve it for me, and it gave me this equation. Pretty powerful, right? Because all we had to do is think about the rate of change. And when we plotted the curve, in fact, this was almost like a trick. We plotted the curve and we said, you know, we want exponential change early on, and we kind of want the rate of change to be 0 at the end. Let's develop a switch over there. And that was it. We didn't even have to worry about the size of the population itself, okay? Now, this is how this formula was obtained. What we did, in fact, is pretty powerful. We developed an equation that describes the rate of change in the population. The solution of this equation was the function that we were looking for, okay? So this entire exercise, you know, we're not going to care about populations, particularly in this course, but this exercise was to motivate you that, you know, why do we need things with rates of change in them? It's because it's actually easier to deal with rates of change rather than quantities themselves. So this leads us to the following, at least leads me to the following conclusions. Is that one, it is generally easier to relate rates of change of quantities together rather than it is to develop an algebraic equation or formula for a specific value of the quantity in question, okay? The second important distinction that you should really ponder on is that the solution of a differential equation is a function, not a number, it's a function, okay? While the solution of an algebraic equation, the solution of an algebraic equation is just a number, okay? Now, the differential equation gives us that algebraic relation with which we can use to get numbers, right? But that's very powerful. Differential equations allow us to develop formulas that make you popular, and you can have your names assigned to them, right? If you find a solution to a differential equation, you can have a formula after your, with your own name on it. So the function that results from the solution of a differential equation, like I said, usually serves as the algebraic relation, as the model that people can use to make predictions. And this is what we do in the vast majority of engineering and engineering science practice, is we develop a differential equation model for how things change in a system and then try to solve that. If we can solve it analytically, you have a formula, your name on it, Nobel Prize, probably, maybe not. But we're gonna also learn how to solve these numerically, okay? So now I'm gonna ask you to actually list some examples now that you're convinced that rates of change, using rates of change is pretty powerful to describe a system. I want you to list a few examples from daily life, from things you know. List as many examples as you can. Take a minute, list as many examples to tell me, pardon me, where you see rates of change around you. Okay, go.
The infection rate of COVID-19.
Yes, but why don't you write it? I'll give you a minute, but yes, you're right. You got about 10 seconds left. I'll give you an extra 10 seconds. See, many of you are writing. All right. Okay, so the floor is open for you to participate and say whatever you think there's a rate of change in. Go.
Cooking.
Cooking, rate of change of what?
Temperature.
Yes. That goes back to the lobster, Connor.
When you're driving, when you're like accelerating or decelerating a car.
Yeah, rate of change of speed, right?
Diffusion of drugs into your body.
Yeah.
Gauss's law.
What is that?
Gauss's law and like the E&M equations, essentially. They're all differential equations.
Okay, I
love Gauss so much.
Oh, physics teachers. No.
Other examples from daily life. Let's think about daily life.
Power, electricity bill.
Pardon me? Can you repeat that, please?
The electricity bill, you're building like kilowatts and
yes,
stuff.
exactly. Your kilowatt hours, the rate of electric consumption. Paul is saying sunlight throughout the day. Absolutely.
Dissipation of pollution in the air. As people stop driving so much.
Yeah, the rate at which that those pollutants dissipate in the atmosphere. Okay.
Say bridges.
Nick, what?
Like bridges. Like I was thinking of like the Tacoma Bridge. I was just thinking of that, but like.
Okay, so that's a disaster. The rate at which the bridge is vibrating, sure, or the rate at which cars are traveling on the bridge. So anyway, flow rate of water through tanks. Yes, absolutely. Okay, Salem. All right. So, it's like I'm preaching to the choir now. There's rate of change everywhere around us, right? I tried to list some examples that I could think of, but I'm not as creative as some of you are. So some of the things I thought about, rate of change of water in a tank. You know, you're like with my kid, sometimes when he agrees to take a shower, you know, he's in the bathtub, and then we fill it, and then he opens the drain, and then, you know, empties all the precious water, and then we fill it again. And so that there's a rate of, you know, water coming in and the rate of water leaving. And I'm trying to keep, as you know, the level close to his ankle as possible, so that he doesn't, you know, get cold. But anyway, so I can rarely match that. Rate of change of population, rate of birth, rate of death, carrying capacity, food availability. When you walk, you're changing your position, right? And there's a rate of change of your position, rate of change of velocity, and rate of change of acceleration with time. Your electric consumption, pandemics, okay, like rate of infection. Someone mentioned the COVID-19. Rate of interest on your loan. Nobody talked about money. So yeah, there's a rate of interest, and the rate of, you know, what's going on with the stock market, kind of the rate of change in the stock market. Completely crazy, right? Rate of growth of your investments, your usage of water, etc. So now I hope that you're convinced that, one, there's rate of change around us everywhere. Two, it is actually easier to relate rates of change. I mean, it does take some mental, some adjustment to think in terms of rates of change, but once you get that figured out, really developing equations becomes your bread and butter. Developing differential equations, and then you use those equations to develop formulas to solve the problems you're considering. Okay. Okay. So that was kind of essentially covering what you probably learned in your math, or what you probably didn't learn in your math. That's the engineering intuitive description of why we need differential equations, and I hope that convinced you that differential equations are very, very important. Any system that changes in time and space is best described by a differential equation. Okay. So now, next, we're going to jump into some more math, get a little bit more rigorous. And again, I'm going to cover things that you probably covered, and only a portion of those, right? I'm not going to cover the entire theory of differential equations that could take us a lifetime. But I'm going to cover some things that, you know, would be relevant. Some you may have seen those or not, doesn't matter. But it's good to kind of reiterate. So we're going to classify differential equations first. And the first classification is going to be a distinction between ordinary and partial differential equations, okay? An ordinary differential equation, as you've noticed, these gray boxes are definitions, right? So when I ask you later on in an exam, etc., you can refer to these boxes, these gray boxes, as these definitions, right? These formal definitions. An ordinary differential equation, or ODE, is a differential equation. So it's an equation that contains derivatives with only one independent variable. So that's the function that we are differentiating. That's the t in the example I gave you, right? This means that an ODE can only contain ordinary derivatives, okay? Sorry, one independent variable, I apologize. It's the one at the bottom. It's not the t, it's the x. So if you only have one independent variable, could be time, could be x, y, something else, concentration, the ODE can only contain ordinary derivatives, not partial derivatives, right? So things like the population growth equation that we looked at with the carrying capacity, filling in the tank or the bathtub, the height of the water in the tank. This equation describes the height of the water in the tank as water comes in and water flows out over the area over the tank. This is the Advection Diffusion equation, which we will also deal with later on in these lectures. A reaction in a reaction mechanism or a change of concentration in a well-mixed reactor. For example, you get something like this. So those are ordinary differential equations. They contain ordinary derivatives because there's only one independent variable. There's only either x or t or y, just one of those, okay? As opposed to partial differential equations, where obviously you have more than one independent variable. You have two or more. So for example, the Poisson equation, d2t by dx squared plus d2t by dy squared equals 0. You have two independent variables, and therefore this is a partial differential equation. And we use partial derivatives in that case because you're differentiating with respect to more than one independent variable. The transient heat diffusion equation, which has time and space combined. In transient advection diffusion equation, again, so we added a second and a first derivative. Doesn't matter how many derivatives you have. What matters is the number of independent variables, okay? Now that we've classified differential equations, let's go through this again, sorry. Okay, next we're gonna classify ODEs. So now we're gonna start kind of homing in on ordinary differential equations, which is going to be the subject of the next several lectures. Okay, so again, we can also classify ordinary differential equations. We can classify those into two categories, what we call initial value and boundary value problems. With initial value problems, also described as propagation problems, you are given the state of the system at an initial time. Again, think of the population. Okay, you have an initial population P0 at t equals 0. The question is, what happens to that population over as time changes, right? So that's what an initial value problem describes. For example, a well-mixed reacting system is described by this initial value problem, for me d by dt, and then, you know, filling the tank. Other examples, population growth, pandemic, disease spread. In other words, anytime you see a derivative with respect to time, that's an indication that this is an initial value problem because time goes in one direction only. Okay, you cannot go back in time, right? So that's an initial value problem. And you will need an initial value, an initial condition for that problem. Okay, as opposed to equilibrium or boundary value problems where you are given the state of the system at physical boundaries. Okay, so you're constrained by two boundaries, and your goal is, at least for ODEs, you're constrained only by two boundaries, right? Because we're one dimension, right? In the independent variable. So you're constrained by these two boundaries, and your question is what happens in the middle. So to give you a more concrete example, remember early on in the course when we were doing iterative solvers, we looked at the example of heat transfer in the wall of our classroom, right? So we looked at the sheetrock, and we looked at the wall, and there was sheetrock, there's some insulation, there's some, and then on the exterior, there's some plywood, and then there's some siding, right? And then the temperature outside is like 10 degrees, let's say in this example, and the temperature on the inside is 70 degrees, and you are to find the temperature distribution, okay, across that wall, right? So you fix the boundaries, you fix the interior boundary because you're heating your interior, and the outside is also just a huge sink, right, or source, and that's fixed at 10 degrees. So you fix those boundaries, and then your question is to find the temperature distribution in between. This is the equation that governs it. It's a boundary value problem. Typically for ODEs, when you have a problem that has space in it, okay, that's a boundary value problem, okay? Because we pretty much all agree that time is always designated by a lowercase t, and space could be x, y, or whatever, okay? Now, some other problems may be a little bit different, may look different, but as long as you have a boundary, two boundaries, this is a boundary value problem, okay? Now we continue with our classification. I'm giving you a couple of other examples, curvature of constrained beams in civil engineering, spring mass systems, as well are sorts of boundary value problems, okay? Now, what's really important is that initial value problems require initial conditions, while boundary value problems require boundary conditions, okay? There's another classification of ordinary differential equations that's not too relevant for us now, but typically, you know, we like to classify things based on the ODEs based on their order. A first order ODE contains only the first derivative of a dependent variable. So for example, d phi by dt equals some right-hand side. And you'll notice as we go along, we're gonna write a generic form, use a generic form for an ODE, and that's d phi by dt or d phi by dx equal to some right-hand side, okay? And that right-hand side could be anything, okay? It cannot contain, if it's a first order ODE, well, it cannot contain derivatives, right? Because the derivatives are put on the left-hand side, and the right-hand side contains, you know, could contain nonlinear terms, functions of the dependent and independent variable itself, but not its derivatives, okay? So a first order ODE could be an initial value or a boundary value problem. Doesn't matter, okay? It's just the order. And you can also deal with systems of equations in that case. And we'll get to this notation in a second. Don't worry about this for now, but you can have many of these equations and you can lump them into a vector, and they could, all of these equations will be coupled, as you will see when we do kinetics, or also when we solve a very interesting problem that I'm going to discuss in the next slide. A second order ODE is one where the highest derivative is a second derivative. Okay, it can contain a first derivative as well, but the highest derivative is always the second derivative. A third order ODE is an ODE with third derivative, and so on. But typically what we do with higher order ODEs is convert them into a system of first order ODEs, because their first order ODEs are much easier to solve, okay? We will also discuss this later. I'm just kind of giving you now some definitions, okay? Now, this equation that I'm writing here is very interesting. It is the advection diffusion equation, and it describes two physical processes happening at two different continuum levels. Advection, and I probably described this earlier in the course, advection is a mechanism. All mechanisms in chemical engineering, they transport information around, okay? Things move, information could be concentration, temperature, pressure, heat, you know, whatever you're dealing with, it's moving it around, moving this information around. And two mechanisms you can describe at the continuum level, and you'll learn about as you go through your courses. And as a reminder, this course is not about developing these equations. So I'll give you these equations, okay? But it's good to kind of start instilling a sense of what you're going to be learning about as a chemical engineer. So these two mechanisms are advection and diffusion. Advection happens at the large scale, at the scale of the fluid moving. So for example, you have, you know, you baked some cookies or an apple pie, right? And then someone is standing away from you. To have them smell it, what would you do? You'd probably blow on it a little bit, right? So that you move the smell of the pie closer to them so they can sense it better, or you put a fan on it, right? So that's advection. Diffusion is essentially if you let that food smell just kind of diffuse slowly in the atmosphere, or like you put a drop of ink and let it kind of diffuse very slowly, take its own time, versus stirring it. If you're old enough to have seen Tom and Jerry or Mickey Mouse, you remember that episode where the lady who, you know, runs the house, owns Tom and Jerry, I suppose, bakes a pie and puts it on the window, and then Tom smells the pie and he kind of, you know, floats around. This is an advection diffusion equation. What I'm showing here now is a uncopyrighted image of Mickey Mouse smelling a pie that's been placed at the window. Now, if you think about it, I'm describing this food smell in the plot below as the x-axis is space and the y-axis is the magnitude of the food smell, okay? So before the apple pie, you know, there's nothing, there's no food smell because the wind is blowing in that one direction. And then as the wind approaches the apple pie, is gonna pick up that food smell and transport it everywhere behind the apple pie. And therefore Tom or Mickey Mouse could smell that and then float towards it, okay? Now what's really cool, and what I just added to these lectures this year, is we are actually gonna model the COVID outbreak using ODEs, rather a system of ordinary differential equations. We're going to use what's called the SIR model, which is susceptible, infected, recovered. I'll teach you about this once we get to systems of ODEs. But this is a solution that I put together just yesterday, showing the effect of the outbreak and based on different parameters. So what we're going to do, for example, we're going to manipulate some of the coefficients in this system of ODEs, okay, to mimic social distancing, for example. So what happens if people social distance? What would happen to these curves? You will see that they'd actually flatten out. So we postpone the peak, but it's going to take longer for people to kind of develop immunity, etc. Then we'll start thinking about ways to looking at, so what if people get vaccinated? What happens to these curves, right? What terms can we add to the ODEs? It's really cool, it'll be fun. So we will do this together once we get to systems of ODEs. But if you look at these equations over here, they're no different than the population growth. And I'll explain to you at one point eventually what these terms mean when you have products of two variables on the right-hand side of an ODE. But these are three ODEs that describe three things. S is the susceptible population. So that's the population that could be infected by the virus. Okay, I is the infected population. So these are the people who actually got infected. So they move from susceptible, they become infected, and then they get recovered, right? R describes the rate of change of people who have recovered. And you see, rather than describing the numbers of people who are susceptible, infected, and recovered, we just look at the rate of change. And we say the rate of change of people who are susceptible moving to becoming infected is a certain rate, which has to do how fast the disease spreads. And then you can manipulate those numbers. It's actually beta over here, that number. And this is where we're gonna manipulate social distancing and see the effect of the policy of social distancing, okay? Right, so I hope this got you excited. So we're not gonna only be doing lobsters, Connor, we're also gonna be doing a SARS-CoV-2 or the COVID-19 outbreak, okay? All right, so then the question is, and now we get into numerical methods, why use numerical methods to solve ODEs? Well, if it's not obvious, actually many problems are very difficult. Many ODEs are so complicated to be able to be solved analytically. And with this, before I embark on numerical methods, I'm going to give you a 2-minute break, as we've been doing. So make sure you mute. Last time I forgot to mute, and everyone now knows, I think, my social security number or like my birth date or something. I had a phone call after the after the exam, and many of you, I forgot to mute the video. Anyway, to mute the sound. So go ahead, take a couple of minutes, and then I'll see you back, and we start looking at why we do numerical methods and how we do numerical methods for ODEs, okay?
My social security number is 6666666.
That's very ominous,
You're
Katrina.
telling me that there's like no 420 in there? What are you, a peasant?
That's true, that's true. Damn it.
All right, so We are back in action, okay? All right, so we left off by trying to argue why do we need numerical methods. What if it's not obvious is that the vast majority of systems, and they are complex, result with nonlinear systems of differential equations or equations. These equations are really impossible to solve analytically. And also, you know, if you forgot how to solve an ODE, it's usually just much easier to hop on Python and program that ODE and just solve it, as we will see, right? Anyway, so there is an immediate need to study how one can solve, how we can solve differential equations numerically. Now, the first thing we're going to look at is the first category of problems. Those are initial value problems. And like we said, they are described by an ODE of the form d phi by dt equal f of t phi, or right-hand side of t and phi. So the right-hand side can contain the independent and dependent variable, and they're always first-order ODEs, okay? And we're going to start by cooking a lobster. Now, there is a historical precedent for this poor lobster that we keep on cooking. It started with Professor Sutherland when he used to teach the course, and I had inherited the slides from him. And then as I developed my own version of the course, I really liked this example and resonated very well with most students. But now I add a footnote that if you're vegetarian, or feel free to substitute everything we're doing next with a vegetable like a zucchini or an eggplant, etc. But for all practical purposes, let's assume we're cooking this lobster, and there's a need to cook lobsters. And apparently there was a report that was recently brought to my light that's found that the population of lobsters is growing exponentially. So e to the RT, R is positive. They're not slowing down. And apparently those lobsters are just wiping out everything of the ocean floor, and they're disrupting the global ecosystems. And so the WHO and CDC have decided, this is a fake report, by the way. Okay, so the CDC and the WA, because I see some people who are surprised. This is not true. It's just setting out an entertaining story for the solving ODEs. Anyway, so the WHO and CDC are recommending that people start eating lobsters as snacks, like mid-morning snack, afternoon snack, to help control the population of lobsters. And actually, that's not surprising. I heard a story on NPR the other day about mustangs, wild mustangs. Apparently, they're growing unboundedly, and now the National Guard or like some military people are going and just kind of try hunting them down because their population is just growing unboundedly. So it's not unheard of for a government or an agency to recommend actually consuming more of a certain population. Anyway, that's not our concern here. Is that the problem is, we have to deal with these lobsters, poor lobsters. Anyway, so you are now tasked with finding the fastest method to cook a lobster, right? So if you want a mid-morning snack, you barely have 2 minutes. Professor Saad gave you, a 2-minute break. You want to cook your lobster very quickly and eat it before you come back to the lecture. So you're now tasked with finding the fastest method to cook a lobster. And you're given two options. You want to boil it in a liquid, could be water, oil, right? Or even maybe put it in an air fryer. Those are becoming popular, or baking it in the oven. So which one is going to be faster, right? That's the question we're trying to address. Now, being a student at the U in chemical engineering, you know how to solve this problem. At least you will know how to solve this problem later on. So what's the fastest method to cook the lobster? We're going to make some assumptions. Again, you're not responsible for these assumptions. I'm just trying to kind of introduce you to what you will be doing in chemical engineering later on, but I will give you the differential equations. Anyway, for the purposes of the story, we're gonna assume that the lobster is a cylinder of size of length L and radius R. Okay, we can specify those. Some numbers I picked up from the market are like 0.3 meters for an average adult lobster from red lobster, and a radius of 0.1 meter on average. And we're going to assume that the lobster remains at a uniform temperature. That may not mean much to you now until you take heat transfer, but that has implications on the equation that we will develop. So obviously, if you were tasked by, doing, I should have done an activity here actually. So let's do an activity now together. Which is going to be faster? Cooking it in a liquid or baking it in the oven? Why don't you take a minute actually and think about this? Okay, which is going to be faster? And why? So cooking it means we want the lobster to reach a temperature, I don't know, 500 for, well done, let's say, okay? Or the vegetable, if you are interested in, eggplants. Now, obviously, if you had a bunch of lobsters laying around in your tank, you just kind of experiment with a bunch of, cooking them and trying to figure out which is faster. But just, as an engineer, what would you say the faster method would be? All right, let's see. So I have some people on chat. All right, Conrad. Air has a lower thermal conductivity. Yeah, okay, so Conrad, what is your answer? What do you think?
I would say that you'd want to boil the lobster.
Okay, why?
Because the thermal conductivity of water is greater than that of air, so you're going to transfer the heat into the lobster faster.
Okay.
It's like the convection versus the.
Yes, that's very correct. However, the answer really is we don't know, because it depends on the conditions of the environment and how high you can get the temperature in the oven, for example. Because the oven is going to cook, we'll discuss this in a second. The oven is going to cook based on radiation, while in water is going to cook based on, like you said, this thermal conductivity coefficient, right? But what if you change the liquid? Okay, what if you change the conditions in the oven? The answer is it's going to depend. Okay, it depends on the properties of the oven you're using, of the liquid that you're using. So there's no generic answer. But how do we get to that answer is we want to develop differential equations for the temperature of the lobster. Okay, we want to look at the rate of change of temperature. Again, going back to Connor, who kept insisting on cooking. Anyway, okay, so we don't know the answer. We want to develop a formula for the temperature, and to get to that formula, we're going to try to find relations for the rate of change of the lobster temperature. Okay, so these are the assumptions just for rigorous, just for being rigorous. You're not responsible for those assumptions, but that's what you will be doing as an engineer, as a chemical engineer. Okay, these are some of the conditions we'll be using in this problem. We're actually going to go and solve it if we have time by today's lecture. Probably not going to have time, but at least we'll set up the problem now. So if you had taken heat transfer, you would know that the governing equation, in this case, based on these assumptions, there are two different equations for boiling or cooking an object in a liquid versus putting it in an oven. In the liquid, the dominant mode of heat transfer is called convection, okay? Where you have to be, essentially, the heat is transferred through the liquid by convective heat transfer, by the motion of the molecules as the water or the oil bubbles around, right? And that's going to be based on the thermal conductivity of the liquid, how well the liquid conducts heat from one molecule to another, versus baking it in the oven where there is air, right? But in the oven, it's a radiation environment. And radiation doesn't actually need a medium to transmit, because in outer space, for example, the mode of heat transfer is radiation. So radiation is an electromagnetic signal that could move heat without the need for molecules, right, in the air, right? The air is going to affect this a little bit through the emissivity, but we're not going to worry about that. We're going to make sure, we're going to assume that you're like in outer space. But then you notice these two equations, they look at the rate of change of the temperature as a function of time. So on the left-hand side, we're looking at d temperature by dt. So that's the rate of change of the temperature with respect to time. But the right-hand side is different for boiling it in water versus baking it in the oven. In the first case, boiling it in water, you see this coefficient, HA over MCP, don't worry about that for a second, times T minus T infinity, okay? Now, what happens for this T minus T infinity? As T approaches T infinity, first, what is T infinity? Sorry. So T infinity is, so once you boil the water or the liquid, its temperature is now going to change, right? because that's where you have this phase transition, right? So the temperature is constant. Once the water is boiling, it's 100 Celsius, or once the oil is boiling, I don't know, it's 150 or something. Okay, so once the temperature of the lobster reaches that T infinity, it's not going to change, right? So that's similar to the population. If you think of the population, if you interpret this equation as population growth, you've reached the maximum capacity of how much heat you can transmit to the lobster, okay? Now the coefficient, most of the terms of the coefficient are fixed. A is the area of the lobster, the cylinder. M is the mass of the lobster. And Cp is how much heat that lobster can contain. We're going to assume it's the heat capacity of water, because most of the lobster, the tissue is what, 70% made of water. So we're going to assume it's like water. But there's one coefficient, H, that we can control. H is called a convective heat transfer coefficient, and it is a function of the fluid in which the lobster is immersed. Like Conrad said, water, let's say you're cooking the lobster in an air fryer versus water versus oil, okay? Each of those are going to have a different heat transfer coefficient, because air conducts heat less than water and water conducts heat less than oil, okay? And so you see in this progression that this H is going to change the rate of change of the temperature in the lobster. So as H becomes higher, you will see that the temperature of the lobster is going to get closer to T infinity much faster. So, you know, we would recommend deep frying the lobster, but it's not going to taste really good. You know, I don't know. I think they do it. I think I've seen it in Tennessee when I was in Tennessee, like they deep fry everything over there. But anyway, so we will look at the different heat transfer coefficients. You know, we will assume that we're frying it in air. We'll pick the heat transfer coefficient for air, and then go through water, and then go to oil, okay? And also, the T infinity is gonna be different for an air fryer, for water, and for oil, right? So that gives us 3 different conditions, per se. Now, when we switch to the oven, also the right-hand side has T and T infinity, but notice the power now, because this is radiation, and you'll learn in radiation when you do heat transfer how to derive this equation, but you have a 4th power in the temperature. So initially, that 4th power is not going to make a big deal, but once the temperature gets higher, this is going to grow really fast. So, you know, once the temperature of the lobster gets to a certain point, it's just going to keep on climbing, okay? Again, when it reaches T infinity, it's gonna slow down, right? And that's just going to not change anymore. But you have a 4th power over there, which could tell you, like, you're not sure which method is going to be faster, okay? Now, the coefficients are pretty much fixed in this case. A and M and Cp are fixed. They're properties of the lobster. Epsilon is called the emissivity. We're going to assume it's 1. It's essentially, you know, is the air blocking your radiation or not? And sigma is a constant, Stefan-Boltzmann constant. That's also fixed. The only thing we can change in the radiation environment really is T infinity. You know, are you broiling the lobster, or are you baking it at 350 or 500, right? And we will look at these different options together, okay? So I think I ran out of time. So next time when we come in class, we're gonna go and solve this directly in Python. And then we're gonna learn, about how Python is doing that, okay? So like I said earlier in the class, we're gonna do this the other way around this time. We're gonna wanna get to solutions first and, describe how, try to solve these 2 equations with different parameters and see which one is going to be faster. I'm going to post these slides just after the class, and feel free to go through the next few slides. There's a Jupyter notebook with gaps on Canvas that I uploaded today. Feel free to download that and try to fill in the gaps, okay, for trying to solve this problem. It's really, we can do this whole thing in like 20 lines of code. We can solve, we can get this solution, okay? So I wish you a good weekend. If you have any questions, feel free to jump in right now. We got maybe a minute. Otherwise, I will release you, and I will see you next Tuesday.
Oh, I actually had a question.
Yes, Katrina.
So can you go back to the slides with the differentiating between 1st order and 2nd order?
Yes, hold on. second order.
Yeah, so I was wondering what makes this, the first order ODE right here, different from a partial differential equation?
So
It seems-
again, a partial differential equation would have more than one independent variable. So you would have the partial phi by partial y, right? Or partial phi by partial x. Let me go to the previous slide. This one, okay? The classification of ordinary and partial. Okay, so you could have a first order partial differential equation, but it would have at least two partial derivatives, one with respect to t and one with respect to x, for example, right? So
that one with respect with x and t for that slide though? Because there was one that was with respect to x and one with respect to t.
yeah, so x and t, it doesn't matter. They're just independent variables, right? So you could have, so for example, the advection equation is partial phi by partial t is equal to partial phi by partial x. And that's a first order partial differential equation, okay? So the order has nothing to do with whether the equation is partial or ordinary. Ordinary means you only have ordinary derivatives. Partial means you have partial derivatives, okay? So, you know, one equation over here could be dt by partial temperature by partial time equal partial temperature by partial x. And that's an advection equation, okay? But it is partial, but in its first order, right? But we're not talking about order of partial differential equations. We're just focused on ordinary right now. So notice the next slide is classification of ODEs, okay?
Okay, sounds good. Thank you so much.
Of course, thank you. Any other questions, comments, concerns?
No quiz today, correct?
Not that I know of. No quiz today.
Okay, that's good.
But please stay tuned to the, make sure you turn on your announcements because you will get a notification if I release a quiz, okay?
Okay.
Okay, all right.
By what time do we have to contact you if we have any partial credit requests?
Yeah, so it's the first slide on the first slide. It's by Friday, April 3rd, tomorrow midnight. Okay.
Okay. Thank you.
Okay.
Do it in video format.
Let me put it April 3rd. Let me type in midnight.
Would it be okay if I did that in video format?
No, please just type it so I have a record of it, and then, you know, when I dedicate time to go through all the cases, I can do them, you know, in one shot.
Okay, sounds good.
But if you want to talk about other things, feel free to just kind of ping me for an appointment, and we can do a Zoom.
Okay.
I mean, which can include the partial credit, but if everyone does it, I'm not going to be able to address anyone's concern, right?
Okay.
So make sure you at least reserve your spot by Friday midnight for the partial credit case. Okay. All right.
Sounds good. Thank you so much.
Thank you everyone for your attention, and I'll see you next Tuesday. Bye-bye.
Bye-bye.